of climate change in the ocean, and specifically in the Hawaiian Islands, like Jim said, because islands have some different concerns that other regions may not experience in the future. Well, okay, I'm not, are you seeing the control panel?
You're back to the edit mode in PowerPoint. I remember yesterday in our test you had something bump on you like this too, but you were able to then.
Okay, we're back. There are many aspects to climate change that we don't consider, and there's many dangerous feedback mechanisms that we can't yet predict. And this is because everything is so interconnected with each other. Due to an increase in atmospheric gases, mainly due to fossil fuel burning, global temperature is on the rise. Now this graph shows a steady increase over the years outside the up and down variation. This temperature increase, among other things, causes thermal expansion of the oceans. And this thermal expansion leads to sea level rise. In fact, it's the #1 contributor to sea level rise, followed by ice and glaciers. A 1 meter or 3-foot sea level rise is predicted within this century. Half of the world's population will live near the coastline within the next decade. Sea level rise will threaten our land and ocean resources. Even if all emissions were to end today, there still would be at least another 2 degrees centigrade rise in temperature by the end of the century. An ocean temperature increase of about 2 degrees can cause corals to lose their tiny single-celled algae zooxanthellae. It provides most of their nutrients and their color. Prolonged and repeated bleaching events can result in mortality. And this has happened in many places worldwide. Reports of widespread coral bleaching have substantially increased over the last decade. Corals can only grow within about 20 degrees south and north of the equator. So you can see this within this band of dots. The red dots show the most severe bleaching in 1998. Now watch as the number of dots increase to 2006. It's increased further. Scientific models predict more frequent and severe bleaching events in the coming years as temperatures continue to increase. In the U.S., there's coral reefs off the coasts of Texas and Louisiana, the Flower Garden banks, reefs off Florida, which have been heavily impacted by bleaching and subsequent disease. And then there are the Hawaiian reefs, and they account for 85% of the U.S. reefs. Not all models make predictive forecasts that are really substantial, but temperature models are the most reliable due to dependable, widespread, and continuous data. A recent model out by the researchers at the University of Hawai'i, where I work, show that the tropics will continuously exceed the current temperature ranges before the rest of the world. In the tropics, small changes are very detrimental because organisms live and have adapted to a narrower range of temperatures. This makes them very susceptible to temperatures outside these ranges. These higher continuous temperatures outside the normal range are predicted to occur by 2043. If there is aggressive mitigation actions that are taken, it will be more like 2069. Poorer countries will be affected first and the hardest. Globally, biodiversity will begin to decline 10 years earlier than the predicted temperature climate departure. Other impacts of climate change will include heat stress-related deaths, increased violence as resources and climate change refugees relocate, a reduced ability to work, and reductions in food production. Up to this point in time, temperatures have increased almost 1 degree centigrade. This chart shows the extensive damage to coral reefs from 0.5 degree to about 2 degrees C. Once temperatures get much higher than that, then the reefs disappear and other species also disappear and other species take their place. These changes are happening more rapidly than at any other time in history. It doesn't give organisms a time to adapt or to acclimate. It doesn't give Earth systems time to come to equilibrium. Another issue for the marine waters has to do with an increase in carbon dioxide. Now, there's been an increase in carbon dioxide in the atmosphere since the Industrial Revolution, but in more recent times, it's been increasing at an accelerated rate. There's terrestrial seasonal variation, so you can see there the red line, the up and down, which is summer, winter, where CO2 is taken up by vegetation in the summer. But overall, the trend is clear, which is that blue line. Atmospheric carbon dioxide, as measured on Mauna Loa here in Hawaii, is steadily increasing. About a third of this CO2 is absorbed by the oceans. Chemical reactions change the pH of the water, and our oceans are acidifying. This ocean acidification will affect the growth of calcifying organisms such as corals, crabs, shells, in favor of non-calcifying organisms like algae. And it will eventually lead to the reefs beginning to dissolve. Temperature and CO2 impacts will spread throughout the entire marine and shoreline ecosystems. One example of potential impacts that's just beginning to emerge include the sea turtles. The gender ratio of sea turtle hatchlings is temperature dependent, just like alligators and crocodiles. When temperatures are warmer, more females are hatched. Global warming could significantly shift towards female hatchlings after about 29 degrees C. Also, many nesting beaches could be inundated with sea level rise, destroying eggs because they're not waterproof, and limiting the nesting habitat. In the Hawaiian Islands, green sea turtles bask. They haul out of the water when the temperatures are colder, and they swim when the temperatures are warmer instead of migrating like other turtles worldwide. So it'll affect them quite a bit. Another species we have here and elsewhere are the hawksbill turtles. And they normally eat sponges, but recently they've been documented eating less sponge and more algae in the last decade, related to the declining coral populations that are associated with sponge habitat. So already the turtle behavior is starting to change. Some species will be able to adapt, but others will not due to the short time span of the change. Sea turtles are already threatened, and the extra pressure of climate change could mean their extinction. Turtles are only one example of the impact to the oceans. Now I'd like to give you a little wider view here before I focus in on Hawaii. So in the Northeast and the Great Lakes region, sea level rise and temperature increase will cause major ecosystem shifts. There will be coastal erosion and flooding in low-lying areas. We'll see loss of wetland habitat affecting migrating and nesting birds. There'll be increased storm surges, which we're already seeing, which will challenge our roads and utilities near coastal regions. Lake and river levels will drop from warmer temperatures, and increased evaporation will lead to declines in fish populations. There will also be effects to shipping and recreational activities, and there'll be a decrease in the water quality, leading to loss of habitat and eutrophication, or too many nutrients in the water. It's been shown that the time from gonad development to spawning is shorter in warmer waters for Atlantic cod, although they grow larger faster at warmer temperatures. So many species will be affected in both negative and positive ways. Sea level rise will also impact the West Coast. There will be less rainfall in some areas, and in others, flooding will occur. We already are seeing increased fires due to drier conditions in some states and flooding in others. The low-lying coastal regions will be inundated with ocean water, and this will accelerate erosional processes. There will also be increased stress on the groundwater systems. We'll see further changes in Alaska. Air temperature in the Arctic have on average increased about 5 degrees C over the last 100 years. And the extent of the Arctic sea ice is decreasing by about 5% a year. Scientists believe that we may be near the tipping point of irreversible change. And there are indigenous witnesses to these changes. Shorebirds and polar bears, seals, and other wildlife have been adversely impacted by these changes. Permafrost thaw and sea level rise that will affect the oceans and coast will damage infrastructure such as roads and utilities. The traditional lifestyles will be altered, and already hunting on sea ice is becoming more and more dangerous. Entire villages face relocation. Increased biological production will occur. Now this may be advantageous to some species, as with larger salmon populations, but as stream flow decreases and habitat is reduced, then the salmon populations will also begin to decline. Serious impacts, such as with the pest outbreaks like the spruce bark beetle that has destroyed millions of acres of forest, have already occurred. In any case, it will seriously disrupt the ecosystem with cascading effects that will affect every trophic level. Different areas will be affected differently by climate change. The Pacific Islands also face serious impacts. Models predict that unprecedented climates will occur earliest in the tropics and among the low-income countries, like I mentioned. Already observed changes include temperature increase, drought conditions, sea level rise, coastal erosion, increased storms, coral mortality, ocean acidification, which leads to economic issues. Now, many of the national parks in Hawaii include an ocean component. And the national parks has a set of talking points to assist with scientific information to answer questions and to help the public to understand climate change. So I'm going to be incorporating some of these more pertinent ones throughout this portion of the presentation. So the talking point number 1, in the U.S. Pacific Islands, average air temperatures have risen by 0.5 degrees Fahrenheit or 0.28 centigrade during the past century. Temperature readings in Hawaii over approximately the last 30 years show strong warming at higher elevations and a rise in surface temperature. The rate of temperature rise at low elevations below 2,600 feet is 1/10 of a degree C per decade, lower than the global rate of temperature increase. However, Hawaii's rate of warming at high elevations above 2,600 feet is 3/10 of a degree C per decade, which is faster than the global rate. The increase in mean temperature in Hawaii is mostly due to a large increase in the minimum temperatures rather than the maximum temperatures. Minimum temperatures have warmed about 3 times as much as maximum temperatures. This means average night and winter temperatures are rising fastest. Invasive species that are better adapted to warmer nighttime temperatures may outcompete native plants. Incidence of malaria in forest birds has more than doubled over a decade in correlation with the summer warmer air temperatures and an increase in mosquito breeding. Hawaiian waters have also shown a warming trend over the past several decades. Average annual sea surface temperatures have increased almost 1.5 degrees C since 1956. We all understand that temperatures have been increasing at alarming rates in the last several decades. What we're just beginning to understand are all the consequences. Even if all emissions were to end today, there would still be a 2 degrees centigrade rise within this century. Now, 2 degrees doesn't sound like much, but let's think about our own temperature. And we're going to switch now to Fahrenheit, because we can understand 98.6 more easily. With the current 1.44 degrees Fahrenheit rise, and another 3.6 degrees Fahrenheit rise, which is the 2 degrees C, which will occur in the next century, your temperature would go from 98.6 Fahrenheit to 103.6 Fahrenheit, and you would already be feeling very sick. And if it were to go on very long, you'd feel major ill effects. So now let's think about corals. Corals live within 1 to 2 degrees centigrade of their thermal maximum temperatures. With a 1 to 2 centigrade rise, they begin to bleach and will eventually die if temperatures remain elevated. And even if all carbon emissions were to end today, the oceans will still continue to absorb a significant fraction of CO2, and temperatures will continue to increase. A third of all coral species are already at high risk of extinction, following widespread losses since the 1970s. In many locations, corals haven't recovered, resulting in cascading effects of decreased fish populations and increased disease. There will be winners and there will be losers in warmer, more acidic oceans, and corals will be among the losers. Declines are happening at different rates in different places with different species. For instance, corals growing in highly variable environments where temperature and pH have wide ranges are showing higher tolerances to temperature stress and other stresses. Now, Hawaii may experience a decline in freshwater resources and overall drier conditions, while at the same time enduring more intense rainstorm events. The state of Hawaii has experienced a decline in rainfall over the past 2 decades, associated with the changes in sea surface temperatures. Historical trends have shown the number of heavy rainfall events decreasing across the Hawaiian Islands. However, the amount of rain falling in the very heaviest downpours is increasing, approximately 12% since 1958. Precipitation events in the Pacific are expected to shift to increased summer rainfall, which is likely to result in increased flooding. This change in reduced precipitation due to warmer temperatures would severely impact vulnerable high elevation ecosystems by reducing groundwater recharge and stream discharge. Hawaii has many microclimates, so large excursions from normal conditions will not be as extreme in all of the regions. As with much of the world, wetter areas will become wetter and drier areas will become drier. However, here in Hawaii, some islands have considerable freshwater subterranean discharge that affects the nearshore environments. This water carries nutrients that affects algal growth and species composition. Some fish species are also associated with brackish water, so disruption in this flow can create shifts in fish, algal, and coral populations. Long-term downward trends have been observed in base flow in Hawaiian streams, corresponding to downward trends in rainfall. This may indicate a decline in groundwater storage and recharge, which has serious implications for drinking water availability, because about 99% of domestic drinking water comes from groundwater. Lower stream-based flows may also limit habitat availability for native stream fauna. The rain that falls today in Hawaii takes 25 years to become our drinking water. It percolates slowly through the island and depresses the salt water beneath it to form a lens, the Geibin-Hertzberg lens. This less dense freshwater lens floats on top of the salt water. Now, the size of the lens depends on the amount of water taken out, the natural discharge, the tides, and the rainfall. Now, as I mentioned, over the past 100 years, rainfall measured in Hawaii, there has been a decrease in the last several decades in rain. When sea level rises and tides are more extreme, ocean water will inundate the freshwater lens, contaminating some of our drinking water. The coastal groundwater table is likely to crop out above ground level and lead to widespread flooding. Sea level is predicted to rise an additional 7 to 23 inches, or 17.5 to 57.5 centimeters, by the end of the 21st century due to thermal expansion, freshwater input, and wind-driven effects, and to continue rising after the turn of the 21st century. The extent of sea level rise differs here in Hawaii from island to island. The varying geologic characteristics of the islands have resulted in sea level rises that have rates between 1.5 inches and 0.6 inches per decade due to the varying ages of our islands and the underlying volcanic rock and the levels of subsidence or sinking. Scientific models predict a sea level rise of over 3 feet within this century. Now this map shows much of how Waikiki will look like in the next 100 years. A lot of it will be underwater. The blue line, as it is referred to, is already moving inland. This is the contour line marking the 1 meter above present day levels. Contrary to popular belief, waves aren't going to be rolling down our streets. Lands lying below sea level will still be dry at low tide and during summers, but when tides are high and when it rains, there will be standing pools of water. At high tides, storm drains will back up and fill with seawater and pour out the storm drains. A present-day example is near the airport in the industrial area called Mapunapuna. When there are heavy rains and high tides, portions flood waist deep because storm drains back up with ocean water and the undercarriages of trucks rust. Even with no rain, it still floods with salt water from surges up the storm drains into the streets. Workers there have found baby hammerhead sharks in 2-foot deep pools in the street, a mile from the ocean, coming up the storm drains. Industrial workers have to time their movement during high tide or during heavy rains. Rising sea levels are expected to exacerbate inundation, storm surge, erosion, and other coastal hazards, which will threaten vital infrastructure, facilities, human settlements, and the livelihood of island communities. This may be particularly pronounced in the Pacific, where reductions in island size may be severe, and where more than 50% of the population currently lives within 1.5 kilometers of the shore. Now, most of our major roads connecting this island, the island of Oahu, are very close to the shore, and many of the other islands. There's already ocean splash during high tides on some of the coastal roads. We will be seeing more road closures, and critical highways will shut down. It will be a huge expense to relocate these roads inland, and large tracts of land will have to be condemned to accommodate inland routes. Travel will have to be timed, and there'll be traffic on the inland roads that will increase. Now, Hawaii's #1 industry, as most of you know, is tourism. And people come to Hawaii to use the ocean resources. In fact, 85% of all people that come to Hawaii use the ocean in one way or another. Beach erosion will seriously affect the economy. With coastal erosion, sedimentation increases on our reefs. And in many areas, it will affect visibility and the abundance of marine organisms. It will also affect important near-shore cultural resources, such as our Hawaiian fish ponds and ancient common shoreline burials. Now, riding on this rising water will be high waves, hurricanes, and tsunamis that will penetrate further and further inland. Land-based structures may be impacted by the storm's stronger winds and rains. Increased intensity of hurricanes and storm surges could damage infrastructure, coastal habitat areas, and even forests. Violent storm events have the ability to wipe out entire forests because Hawaiian plants have adapted over thousands of years to historical weather patterns. As intensity and frequency of storms gets stronger over a relatively short period of time, there is little time for these forests to adapt to these new conditions. And similar to the forests are antiquated stormwater drainage systems that divert surface water off the land to prevent flooding have also been developed for past conditions. Additional loss of land due to increasing frequency and intensity of storms, sea level rise, and other changes in oceanographic conditions will further threaten the endangered monk seal and our turtle populations. All of these issues are closely linked with the economy. Major economic impacts will come from increased storms, coastal erosion, declining reefs, sea level rise, drought, and flood conditions. Hawaiian coral reefs will be increasingly vulnerable to large-scale bleaching if the current trend of increasing temperatures continues. Shallow areas with little water circulation will be most affected and will likely experience increased mortality, while open coastal areas adjacent to deep oceanic water are likely to be the last affected. Higher ocean temperatures will also cause widespread bleaching. Corals depend on that tiny single-celled algae, zooxanthellae, to give it nutrients and color. And when temperatures rise, these zooxanthellae are not in the corals anymore. The corals turn white, called bleaching, and eventually they'll die if temperatures don't return to normal. Now, a colleague of mine, Dr. Paul Joe, first described bleaching in response to an electric generating station in 1970 here in Hawaii, and observed the first natural bleaching in 1974 in Aniwika. In manipulative experiments, he and his colleague, Dr. Steve Coles, stated that corals live within 1 to 2 degrees centigrade of their upper summer limits. Now, he said this in the 70s, and it still holds true today. All over the world, whether you're in the Arabian Gulf, where mean summer maximums are 34 degrees centigrade, where the bleaching threshold is 35 to 36 degrees C, or if you're in Hawaii, where summer maximums are 27 to 28 degrees C, and they bleach at 29 to 30 degrees C. So if you look at the column increase above summer maximum, it's all 1 to 2 degrees above summer maximums all over the whole world. It still holds today. Corals will bleach 1 to 2 degrees above summer maximums. We had a major bleaching event in the main Hawaiian Islands in 1996. Then again, in 2004 and 2006, the corals in the northwestern Hawaiian Islands, our uninhabited chain of islands that stretches 1,500 miles northwest of the main Hawaiian Islands, experienced major bleaching. We were fortunate that the temperatures returned to normal and most of the reefs recovered, but these events are predicted to occur more frequently and be more severe in the coming decades. Bleaching can occur from many stressors, including sedimentation like you see here. But with temperature bleaching, it's not only temperature dependent, it depends on other factors as well, such as water quality, where the clearer waters, sunlight can penetrate deeper and more intensely. It also depends on water motion. The ideal conditions for coral bleaching are calm waters, high irradiance, high temperatures, and high visibility. This makes for good coral bleaching times. Just like with people, when corals are stressed, they're more susceptible to disease. Our reefs will see a higher prevalence of disease like what happened in Florida and the Caribbean. Many marine organisms depend on coral reefs. A trophic cascade will occur where coral-associated fishes will disappear and many of the invertebrates that depend on corals. In the next 50 years, temperature and carbon dioxide levels are predicted to increase beyond levels that coral reefs have experienced over the past 500,000 years. Carbon dioxide in the atmosphere, mainly due to fossil fuel burning, like I said, is absorbed by the oceans. And it changes the water chemistry, and it lowers the pH of the water, or the number of hydrogen ions in the water. Research from our long-term mesocosm experiments show that levels of ocean acidification predicted to occur within this century demonstrate a decrease in calcification in Hawaiian corals by 15 to 25%, which is similar to coral species elsewhere. So corals will not be able to calcify as easily. Now we stained these corals with a biological stain known as alizarin red, and you can see the stained corals here and the amount of growth that occurred in the 10-month period after they were stained. The corals on the left of the screen were under acidified conditions that will happen in 50 years, 2 times the PCO2, or the partial pressure of carbon dioxide. The coral on the right, you can see a large amount of growth in the white area after the pink area, and those were under normal present-day conditions. Well, we found no mortality, the reduction, like I mentioned, of 15 to 20%, and that corals will be less dense, more porous, with thinner branches under acidified conditions, increasing susceptibility to breakage. And we saw no evidence of acclimation over this 10-month period. Corals and other organisms make their skeletons out of calcium carbonate, but not all calcium carbonate is created equal. Corals make a structure of aragonite, while some organisms create high magnesium calcite skeletons. Organisms like calcareous coralline algae that you see here. This calcareous coralline algae cements our reefs together, and it provides a substrate for corals to recruit upon. It's very important in the environment. Corals, what we found was that calcareous coralline algae will be affected by ocean acidification sooner than organisms like corals. We found that recruitment and growth of crustone coralline algae will decline by over 90%. Higher latitude environments and associated cold water are at greater risk of acidification. Now this is due to a thermocline that's close to the surface, creating stratification. The warm surface waters are very thin there, and upwelling occurs, bringing that colder, deeper water up. These waters hold more CO2, similar to a soda. A cold one is more carbonated than a warm one. However, light and temperature will have more of an impact on reefs than ocean acidification. But let's look at the combined effects. These are called synergistic effects. There are local impacts such as overfishing, increased pollution, sedimentation that will lower the resistance to these global impacts. But sea level rise will add sediment to reefs where light is blocked and larvae can't settle. Thermal stress will cause bleaching and mortality, and ocean acidification will eliminate the reef structure. Corals will bleach, some species will be eliminated, coral skeletons will be more fragile, the reef structure will begin to dissolve, and boring organisms, such as some sponges, urchins, and bacteria, will begin to erode the reefs from the inside and the out. In some areas, the carbonate structure will erode down to the volcanic foundation. Now last year, in 2012, we resurveyed all our coral reef assessment and monitoring program sites. We have over 60 long-term monitoring sites and 200 rapid assessment sites. And we have these all over the main Hawaiian Islands. Overall, we found that the mean statewide coral cover and diversity did not show a statistically significant change since the initial surveys 14 years ago, although local variations were detected. So you can see the coral cover in 1999 was 24.3% average throughout the state. And in 2012, last year, it was 24.1%. There really wasn't much of a difference overall. The island of Maui, though, reports the most statistically significant declines. And this has been linked to land-based nutrients and low herbivore populations. At sites with low fish grazing, mainly due to heavy fishing pressure, algae competes with coral for substrates as well. Steady decline at sites with open access on Maui are related to chronic localized anthropogenic impacts or human-based impacts, while marine protected areas and deeper sites like Molokini, a little island off of Maui, are further from land-derived materials, and they remain stable. or experience slower declines. Hawaii has escaped the major climate change-related reef damage that has occurred in other regions. Most Hawaii reefs are located on island slopes near deep oceanic waters with high wave energy that flushes sediments and pollution from the system, and it moderates temperatures. Also, Hawaii is relatively free of industrial development, mining, and other really highly polluting activities, although sediment impact does result from improper land use practices, and feral ungulates is a major problem on some islands, like South Molokai has a sedimentation problem, and Lanai. Although over half of all reefs in the wider Pacific region are currently listed as threatened by the World Resources Institute, Hawaii has one of the lowest threat ratings overall. The main Hawaiian Islands, as you can see from this slide, occupy a unique geographic position in an area of the north central Pacific that has escaped major bleaching events, as well as rapid sea level rise over the past decade. In addition, as the bleaching threshold was approached in 1996, there was a reversal of the warming trend that can be attributed to the Pacific Decadal Oscillation. That's the PDO. Now, the PDO has been described as a long-lived El Nino-like pattern of the Pacific climate variability. The PDO is characterized by widespread variations in the Pacific Basin and North American climate. The phases of the PDO have been classified as being either warm or cool. Now, during the past century, two major PDO eras that have persisted for 20 to 30 years have been identified. Cool PDO regimes prevailed from 1890 to 1924, and again from 1947 to 1976, while warm PDO regimes occurred from 1977 through the mid-90s. There was a downturn of seawater temperature off Hawaii in 1975 and 1998 as the PDO reversed. The global sea surface temperature pattern highlights the strong tendency for temperatures in Hawaii and the central North Pacific to be unusually cold when sea surface temperatures along the coast of North America are unusually warm, and vice versa. Prediction of changes in local sea surface temperature becomes uncertain whenever there's a change in the PDO pattern, such as took place in 1998 at the end of the 97-98 El Nino. Because of the uncertainty of how the PDO works, it's not possible to say that the recent decline in warming in Hawaiian waters, that it hasn't declined, marks the beginning of this 20 to 30 year cool phase of the PDO. But it may explain this downturn and why we're not seeing so many changes. There's a continuing increase in mean global temperature, which will continue as humans add additional greenhouse gases to the atmosphere. So a cooling phase in Hawaiian waters will only serve to moderate the local warming trend during the first part of the PDO cool cycle, but will accelerate warming when the cycle reverses. Thus, the overall statewide coral cover and diversity that has remained relatively stable since the initial coral reef assessment and monitoring program surveys have shown this, while coral cover on reefs such as in the Caribbean have declined by 80% since 1977 due to bleaching events, storms, disease, and a major decline in coral growth. Nevertheless, Hawaii and other areas of the Pacific with relatively healthy coral reefs are now at a threshold of severe and frequent bleaching events projected for the near future, within the decade. This model shows what the bleaching events projected are for the near future. You can see bleaching events in the world for the 2030s. I have the Hawaiian Islands circled here. And in the 2030s, there will be between 30 and 70% of all years that will have a bleaching event. This is what that means. By the 2050s, Hawaii will experience bleaching events in 80 to 100% of the years, nearly every year. 70% of this planet is ocean. It drives the weather and climate, it stabilizes the temperature, it generates most of the oxygen in the atmosphere that we breathe and absorbs much of the CO2. 50 years ago, we couldn't even imagine that what we did to the ocean would make such a difference. We believed it was way too big. 50 years in the future, it will be too late. This means that we're at a pivotal place in history where the decisions that we make in the next decade will determine the direction of our future. We've already lost nearly half of the world's coral reefs, but the good news is that half of the coral reefs of the world are still in good shape, including many of Hawaii's. Sound management strategies based on scientific research will increasingly play a more and more important role in the future of the world's reefs. It will take a global effort to minimize the effects of climate change, but if we all work together, we can make a difference. The American scientist Margaret Mead said, "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." It always starts with passionate individuals. Only then can it spread to larger entities like corporations and governments. You can help lessen the carbon impact on the reef. When you think about the true cost of everything you buy, the cost to the environment. How was it made? How far did it have to come from? Try to buy local foods that aren't associated with the large carbon travel costs. Eat lower on the food chain. It takes 10 times more energy each level you go up the food chain. For instance, it takes 10 pounds of corn or soybeans to make 1 pound of beef or pork, or 10 pounds of an herbivorous fish, a fish that eats algae, to make 1 pound of a piscivorous fish, a fish that eats other fish. Just eating a more healthy diet will help reduce your carbon footprint. We can also become part of the solution by developing and using new Earth-friendly technology. Once we're making more conscious decisions about living sustainably, we take that first step in securing our future. I believe that if we all work together, we can, as Gandhi so eloquently put it, be the change we want to see. Mahalo, and thank you for listening.
All right, thank you very much, Ku'ule. It's a very interesting and comprehensive presentation of climate change issues. If you do have questions, there should be a question box available in your panel, the webinar, the GoToWebinar software panel. So feel free to type those questions in, and I will read them to Ku'ule, and she could answer. Here's a question about coral reefs specifically. As coral reefs bleach and disappear, you referred to both, winners and losers in climate change. What is the winner? What moves in and sort of takes over that space?
That's a good question. There are going to be phase shifts, and it's going to be different in different areas, but overall, it's going to be algae. So a lot of the fleshy type of algae, also the turf algae or the smaller little types of algae on the reef. Bacteria does very well in warmer waters. So you're going to see more bacteria and other organisms that are filter feeders, organisms that don't calcify. All the non-calcifying organisms may do better. Certain types of fish may do better. The type that are herbivores, the ones that eat algae, those types of fish may do better. You see more and more of those fish, and less corallivores, the ones that eat corals exclusively, or those that are omnivores that eat different types of mixed diets, and invertebrates that are associated with the reefs. And then the tuna are the deep and all the deeper sea organisms, the pelagic fish. They're expected to decline as well. As the oceans get warmer, some organisms like the six-gill shark. There will be more of those and less tuna, mahi in most areas. It seems that that California coastline has that cooler waters and won't be as affected. There will be more pelagic fish there, but other places throughout the Pacific will have less. And part of the reason for this is that the oxygen levels in the oceans are depleting. And so fish like tunas are very high metabolism fish. They move really quickly. They have to have a lot of oxygen, so they stay within that oxygen level. But fish like the six-gill sharks spend a lot of their time deeper in areas that are hypoxic or have little oxygen.
Okay, and a follow-up to that is if those areas become more dominated by algae and bacteria, is there indication that that ecosystem would be less biodiverse, or do we really know the answer to that?
We do know the answer to that. There may be a shift in species, and there may be a lot more of the algal species, but it has been shown by scientists that biodiversity is already declining and will continue to decline, not only in the oceans, but on land.
Okay, and here's a question regarding, you showed the dramatic image of, I believe it was Waikiki, what it could look like in sea level rise scenarios. What is the sort of government and local populace, reaction to that? Are there mitigation or adaptation efforts, serious ones underway?
Hawaii has been at the forefront, and for good reason. We are supposed to be 70% renewable and sustainable by 2030, both in electricity and transportation. We have this Hawaii Clean Energy Initiative that's a joint agreement between our governor's office and the U.S. Department of Energy. And we have done a lot of solar, a lot of renewable energies such as geothermal, which is producing superheated underground steam from volcanic activity, hydropower from streams, biomass for generation and conversion into fuels. We have OTEC, ocean thermal energy conversion, where we take very cold water from deep on the Kona coastline, and we can bring it up and use it for energy and air conditioning. A lot of photovoltaics now, and Hawaiian Electric, our company here that serves the islands, is increasing not only their photovoltaic system that hooks us in, which I do have a full system, but also wind. There's several large wind farms that are increasing, and then waves and currents. We have a lot of things here in Hawaii that can really make a difference. It's funny because I used to say, 15 years ago, that there are problems in the ocean we have to take care of in the ocean. We have to be careful not to anchor on the coral reefs, not to step on the coral reefs, not to overfish. And I stopped doing that. The answer is on land. We have to reduce our carbon emissions.
Okay, very good. Thank you. Again, Ku'ulei, unless there are any more questions, I'm not seeing any more in the box right now. I really appreciate your time and for sharing your expertise with us. And as I said, the webinar was recorded, so it'll be up on the Ocean Alaska Science Learning Center website not too long from now, should be within a week or so. And if no more questions, I guess our next webinar that we have planned is not until January. We're going to take a month off. The whole holiday season gets a little challenging for folks, and we'll be back with another talk on ocean acidification and ocean currents on January 23rd. At least that's our scheduled one now. We'll certainly send out word and let everybody know. And thanks again, Ku'ulei.
Okay, aloha and mahalo. Thanks for the opportunity.